dear students, this is a continuation lecture for the some basic concepts of chemistry. In the third part we have learned about the laws of chemical combination. In this video we are going to discuss about atomic mass and molecular mass. Some basic concepts of chemistry. Some basic concepts of chemistry from this chapter. This is a fourth video, fourth part. In this video we are going to learn about atomic mass, and molecular mass. Atomic mass and molecular mass. Students, for example, when the atomic mass of sodium is asked, right? Atomic mass, there is no difference in the mass and the weight in the chemistry. Atomic weight, we can also call it as an atomic mass. Atomic mass of sodium, when we are asking, it is a 23. Simply we will tell some number 23. Atomic mass of oxygen, it is a 16. Atomic mass of calcium is 40. So all these masses we are expressing as a numbers. These are relative masses. Okay. With by taking some standard, comparing the weights of the elements, these are known as relative atomic masses. So generally atomic mass of an element is, it is a number. Relative atomic masses only we are using. Scientists earlier they are using hydrogen scale. Hydrogen scale, what is the standard is? 1 atom of hydrogen is a standard. Atomic weight of an element is weight of one atom of an element divided by weight of one atom of hydrogen. So students, here one atom of hydrogen. Here standard is 1 atom of hydrogen, weight of 1 atom of hydrogen. So that means atomic weight of an element is how many times it is heavier than 1 atom of hydrogen. This is atomic weight, whatever we are considering. These are relative atomic masses. Later it has been replaced with the oxygen scale. Oxygen scale. Reason why this hydrogen scale is replaced with the oxygen scale is reactivity of oxygen is more than hydrogen. So hydrogen, compared with the hydrogen, oxygen will form more number of compounds with the most of the elements in periodic table. So later that hydrogen scale has been replaced with the oxygen scale. On the oxygen scale, atomic weight of an element is mass of one atom of an element divided by 1/16th part of 1 atom of oxygen. 1 atom of oxygen. Here the standard weight is 1/16th part of 1 atom of oxygen. Right? So finally, IUPAC has declared it is better we can consider International Union of Pure and Applied Chemistry, that has been declared that better we can use 1/12th part of 1 atom of carbon 12 as a standard. why the oxygen scale has been replaced with the carbon scale is when we are calculating the relative atomic mass of an element for most of the elements on the oxygen scale, for most of the elements on the oxygen scale, relative masses, relative atomic mass, we are getting it as a fractional values. So oxygen scale is replaced with the carbon scale because here for most of the elements we are getting relative atomic masses as a fractional value. So finally nowadays also we are using carbon scale as a standard. What is a standard value? That is generally represented as 1 atomic mass unit, that is 1 by 12th part of 1 atom of carbon 12. Let us discuss what is a AMU. Students, 1 AMU is equal to 1 by 12 into 1 atom of carbon 12 is 1.9926 into 10 power minus 23 grams, which is measured from the mass spectroscopy technique, right? So on simplifying this, we will get a 1 AMU atomic mass unit is equal to 1.66 into 10 power minus 24 grams. We will get. Recent days, this is called as unified mass. AMU is replaced with the term that is a unified mass. So on the carbon 12 scale, atomic weight of an element is equal to mass of one atom of an element, divided by 1 by 12th part of 1 atom of carbon 12. So the relative atomic weight of an element is how many times it is heavier than 1 by 12th part of 1 atom of carbon 12, which is known as 1 AMU atomic mass unit, which is recently we are calling it as a unified mass, right? Generally students, for some of the elements we will take average atomic weight. For some elements in calculations we use average atomic weight because the element will exist more than one isotopic form, because that element exists in nature in more than one isotopic form, right? So for example, if you take chlorine in the nature, it will exist as two isotopic forms. Chlorine Cl 1737, right? The percentage abundance of Cl35 is 75% in the nature. This is percentage abundance of Cl35 is 75%, Cl37 is 25%. So average atomic weight of chlorine is, the percentage abundance is 75 into atomic mass of this isotope 35 plus average abundance of the other percentage is 25, other isotope, its atomic mass is 37 divided by 100. So by simplifying this, we will get it as average atomic weight of chlorine is 35.5. Generally, in all calculations, we will use atomic mass of chlorine as 35.5. Right? So, general formula for average atomic weight. Average atomic weight is mass of isotope 1 multiplied by its abundance plus mass of isotope 2 into its abundance if it exists more than 2 isotopic forms and so on, divided by 100 will give us average atomic weight. This is generally used for the element for which in the nature they will exist in the more than one form. Isotopes these exist, right? Next is molecular mass. Molecular mass is sum of masses of all the atoms present in a molecule Students, for example, if you take H2SO4, sulfuric acid, molecular weight of sulfuric acid is, it has 2 hydrogen atoms. 2 into 1 hydrogen atom weight is 1 plus sulfur, only 1 sulfur atom it is there. 1 into atomic weight of sulfur is 32 plus 4 oxygen atoms, 4 into 16. So this total we will get it as a 98, right? Atomic weight of H2SO4. Atomic weight is same as a molecular weight. Molecular weight of H2SO4 is same as a molecular mass, right? For acetic acid CH3COOH, it has 2 carbon atoms. So molecular weight of acetic acid is 2 carbon atoms are there, 2 into 12 plus 4 hydrogens, 4 into 1 plus 2 oxygens are there, 2 into 16, right? 2 into 16. Total we will get it as a 60. So the sum of masses of all the atoms present in a molecule, that is known as molecular mass or the molecular weight, right? If it is sucrose, C12H22O11, right? So molecular weight of sucrose is cane sugar. C carbon is 12 atoms, 12 into 12 is the atomic mass of the carbon plus 22 hydrogens, 22 into 1 plus 11 into 16. You will get this as a 342. Molecular weight of sucrose is 342. We are getting, right? So for ionic compounds, we won't use a molecular mass, we will use a formula mass. Formula mass is generally used for the ionic compounds. It is used for ionic compounds. It is used for ionic compounds. This is a mass of all atoms present in one formula unit. So why we are using formula mass for the ionic compounds? Let us discuss now. Students, for a ionic compound like NaCl, CSCl, we should use a formula mass instead of using molecular mass or the molecular weight. For example, if it is a sulfuric acid H2SO4, which is a liquid at room temperature, the smallest unit of the sulfuric acid is 1 molecule one molecule, right? H2SO4. So in these type of compounds we can use a molecular weight, right? Molecular weight we can use. For the ionic compounds, like for example NaCl you take, which has the unit cell FCC structure. In the solid state chapter we will learn in detail about the FCC structure there, right? So here in the one unit cell, the smallest unit of the compound like H2SO4 is one molecule. But whereas for the NaCl like ionic compounds, the smallest unit it is called as a unit cell. And type of unit cell for the NaCl is FCC. This is for the NaCl. Okay. All the corners is occupied by Cl minus ions. All the corners, a cube has 8 corners. 8 corners is occupied by 8 Cl minus ions. And 6 phase centers. A cube has 6 phase centers. Right? This side, opposite side, top face, bottom face, front face. This is the back side face. 6 faces are there, right? And I am representing the Na plus with the red color, right? Here body center 1, all edge centers it has 1 Na plus. A cube has 12 edge centers. The cube has 12 edge centers, right? Then if we calculate the effective number of Na plus 1 is present inside the body center. This will represent only to the particular unit cell because inside the unit cell. But one ion which is present at this is edge center, it is equally shared between 4 unit cells. So like that 12 edge centers, 12 Na plus atoms are there. Each is equally shared among 4 unit cells. So this total we will get it as 4 ones are 4 threes are 3 plus 1 is 4. Similarly, we will calculate the effective number of Cl minus. Here, what is the location of Cl minus? 8 corners. 8 corners. Corner ion contribution is 1 by 8 because one atom or the ion which is present at the corner is equally shared among 8 unit cells. So 8 into 1 by 8 plus 6 phase center. Phase center contribution is 1 by 2. So this is 8 gets cancelled. 2 ones are 2 threes are 3 plus 1 is 4. So one smallest unit of NaCl crystal, that is a unit cell, right, which will represent 4 formula units. One unit cell of NaCl represents 4 formula units. 4 formula units. Whereas when we take a CSCl which has a BCC structure, one unit cell represents only 1 formula unit. One unit cell represents only 1 formula unit. Here 8 corners of the cube is occupied by 8 Cl minus ions. 8 Cl minus ions. Right? These are Cl minus. And the Cs plus I am indicating with the 1 is present only at a body center, that is the Cs plus. So here 1 unit cell represents only 1 formula unit. Only 1 formula unit. So that's right. For the ionic compounds, generally we will express the mass as formula mass instead of using molecular mass. Thanks for watching.